How far could humans actually travel through space in one lifetime? At this moment, the quickest machine our species has ever produced is racing through space at roughly 430,000 miles per hour. At a speed that's almost impossible to picture, it could loop around Earth in less than 4 minutes. And yet, even moving that fast, even at a velocity that would instantly destroy anything human that touched something solid, this same spacecraft would still need more than 6,000 years to arrive at the nearest star. This is the point where our everyday ideas about space travel begin to fall apart. The true limit on how far a person can travel in a single lifetime isn't really about technology, budgets, or determination. It's set by something far deeper, a boundary stitched into the very structure of reality itself. And yet, inside that boundary, there exists a remarkable escape route, a loophole so extraordinary that it could, in principle, allow a human to reach regions millions of light years away, while only experiencing the passage of a few decades. If you're curious about just how far one human life might truly extend across the universe, and you enjoy exploring ideas like this, please consider liking and subscribing. It genuinely makes a difference. Are you ready to dive in? Let's start. The fastest object ever built by human hands is currently tearing through space at a speed that defies ordinary intuition. The Parker Solar Probe, launched in 2018, has reached velocities beyond 430,000 miles per hour during its closest sweeps past the Sun. At that pace, it could travel from one side of the continental United States to the other in under 25 seconds. It's moving so rapidly that if you were standing in New York, you could blink a couple of times and the spacecraft would already have crossed Los Angeles, surged out over the Pacific Ocean, and be heading toward Hawaii. This achievement stands as one of the most extreme demonstrations of what human engineering has ever accomplished. After decades of technological refinement, billions of dollars poured into development, and the shared knowledge of thousands of scientists and engineers, the Parker Solar Probe uses a carefully planned sequence of gravitational assists from Venus to reach speeds no chemical rocket could ever generate on its own. With each close pass, the spacecraft siphons off a minute fraction of the planet's orbital energy, slowly and deliberately increasing its velocity over years of precise trajectory tuning. The probe stands as humanity's most ambitious attempt to move swiftly through the emptiness of space. To truly grasp how extraordinary this speed is, it helps to look back across the entire timeline of human motion. For the vast majority of our species' existence, the maximum speed a human could reach was about 25 miles per hour, the fastest pace of a galloping horse. That ceiling remained in place for more than 200,000 years of human history. By 1900, automobiles began exceeding 60 miles per hour. In 1903, the Wright brothers achieved flight at 3-4 miles per hour. Just 60 years later, test pilots shattered the sound barrier at 761 miles per hour. Then, in 1969, Apollo astronauts returning from the Moon reached nearly 25,000 miles per hour, the greatest speed ever experienced by a human being. The Parker Solar Probe travels 17,000 times faster than those Apollo astronauts. It moves at a velocity so extreme that no human could survive on board, not because of the speed alone, but because its path brings it close enough to the Sun to endure temperatures above 500 degrees Fahrenheit. This is not speed produced by brute engine force, but by decades of gravitational choreography. Even so, this astonishing velocity exposes a harsh reality about our limits in space. Moving at 430,000 miles per hour, the Parker Solar Probe would still need roughly 600 years to reach Proxima Centauri, our nearest neighboring star, located just 24 light-years away. Put into human perspective, a voyage that began when the ancient Sumerians first developed writing would only now be nearing its end. A typical human lifespan lasts about 80 years, at humanity's highest achievable speed. That means you would travel barely more than 1% of the distance to the closest star before your heart delivered its final beat. The numbers grow even more unsettling when you calculate what a single human lifetime actually covers at these record-breaking speeds. Maintaining the Parker Solar Probe's top velocity for 80 years would take you about 3 trillion miles. Written in full, that figure contains 12 zeros. It feels unimaginably large until it is compared with the real scale of space. 3 trillion miles amounts to only about 0.5 light-years. The nearest star system lies more than 80 times farther away than what an entire human lifetime at maximum speed could traverse. You could spend your whole life in motion and still never come close to escaping our local stellar neighborhood. The Oort cloud offers another sobering benchmark. This distant, icy shell of ancient comets defines the outer boundary of the Sun's gravitational reach. It stretches out to as far as 100,000 astronomical units from the Sun, with 1 astronomical unit being the distance between Earth and the Sun, roughly 93 million miles. The Oort cloud marks the true edge of our solar system, where the Sun's gravitational hold finally fades and genuine interstellar space begins. At humanity's current maximum speed, reaching even the inner edge of the Oort cloud would take about 600 years of uninterrupted travel. A full human lifetime, even at unprecedented velocities, would fail to break free from the Sun's extended gravitational domain. We would perish long before departing the Sun's vast family of orbiting debris. Measured against the true scale of even our nearby cosmic environment, the total distance covered over an entire lifetime would be comparable to traveling from Manhattan to Brooklyn. To see what decades of real space travel amount to, consider the Voyager 1 spacecraft. This extraordinary probe has journeyed farther from Earth than any other human-made object ever built. After more than 47 years of continuous travel through interplanetary space and now into interstellar space, Voyager 1 has covered approximately 15 billion miles. Reaching that distance required nearly half a century, and even now, the spacecraft continues extending its record with every passing second. Voyager 1 crossed the heliopause in 2012, formally stepping into interstellar space. This boundary is the region where the Sun's solar wind finally yields to the pressure of the interstellar medium, the extremely thin mix of gas and dust that occupies the space between stars. News headlines announced that Voyager had left the solar system, a statement that is technically correct in one respect, yet seriously misleading in another. The spacecraft has escaped the Sun's magnetic influence, but it is still securely bound within the Sun's gravitational reach. It will not move beyond the Oort cloud for another 30,000 years. A distance of 15 billion miles sounds extraordinary, until you realize that it amounts to less than 0.03% of the distance to the nearest star. If the trip to Proxima Centauri was scaled down to a cross-country drive from New York to Los Angeles, roughly 2,800 miles along the highway, Voyager 1 would have traveled only about 100 feet in 47 years. You would still be standing in your driveway, barely past the mailbox. Even after half a century of non-stop driving, your neighbors would watch you grow old, from youth to retirement, while your car never left sight of their kitchen window. There is another way to understand this imbalance. Light travels at 186,000 miles per second. In the time it took you to read this sentence, light has gone far enough to circle Earth 7 times. Voyager 1, after almost 5 decades of flight, has covered a distance that light crosses in about 20 hours. The probe's 47-year journey amounts to less than a single day of travel at the speed of light. The 4-year journey that light takes to reach Proxima Centauri represents more than 150,000 times the distance Voyager has managed in nearly half a century. Voyager 1 moves at approximately 38,000 miles per hour relative to the Sunday. That speed, astonishing by everyday standards on Earth, exposes the immense gap between what humans can achieve and what the cosmos demands. At this pace, the probe would require more than 70,000 years to reach Proxima Centauri. By the time Voyager 1 ever reached the distance of our nearest star, assuming it somehow survived the hazards of interstellar space, the humans who built and launched it would have been extinct longer than our entire species has existed so far. Homo sapiens emerged roughly 300,000 years ago. Voyager would need to travel for nearly a quarter of that entire span just to arrive at our closest stellar neighbor. The probe will not complete that journey. Voyager 1 is powered by a plutonium-based energy source that generates electricity through radioactive decay. This power supply loses approximately 4 watts each year as the plutonium gradually decays. By 2025, the spacecraft will no longer have enough power to run any of its scientific instruments. By 2036, it will go completely silent, continuing onward as an inert relic drifting through space. It will wander for tens of thousands of years, a quiet testament to human ambition, never reaching a destination, never again being observed by human eyes. At the core of this problem is the physics of chemical propulsion. Every rocket humanity has ever launched relies on the same basic idea that lifted the first Chinese fireworks into the air more than 1,000 years ago. Hot gas expelled in one direction pushes the vehicle in the opposite direction. It is Newton's third law in its purest form. You throw mass backward, and the reaction force moves you forward. An elegant and powerful principle that is also brutally inadequate for interstellar travel. Chemical rockets are constrained by an unavoidable limit embedded in the Tsiolkovsky rocket equation. This relationship, formulated by Russian scientist Konstantin Tsiolkovsky in 1903, defines the maximum speed a rocket can reach based on 2 parameters. The first is the exhaust velocity of the propellant, essentially how fast the rocket can eject material from its engine. The second is the ratio between the rocket's initial mass, including all of its fuel, and its final mass after that fuel is burned. For chemical fuels, exhaust velocities top out at about 4.5 kilometers per second. This is not an engineering shortcoming waiting to be solved. It is a fundamental limit set by the chemistry of combustion itself. When hydrogen and oxygen burn, the most energetic chemical reaction we can realistically use in rockets, the resulting steam molecules can only move so fast. The energy released by breaking and forming chemical bonds has an absolute ceiling, and no amount of clever engineering can force water molecules to leave a rocket nozzle faster than chemistry allows. The harsh reality of the rocket equation becomes painfully obvious when you calculate what even modest interstellar speeds would demand from chemical propulsion. To accelerate a small probe with a mass of just 1,000 kilograms to 1% of the speed of light using chemical rockets, the required starting fuel mass would exceed the total mass of the observable universe. Not the mass of Earth, not the mass of the Sun, not even the combined mass of all the stars in our galaxy. The combined mass of every galaxy, every star, every planet, and every atom across the entire observable universe would still fail to provide enough chemical fuel to push a small car to just 1% of the speed of light. This isn't a figure chosen for shock value, nor is it an overstatement designed to sound dramatic. It is simply the outcome demanded by the mathematics. The rocket equation includes an exponential term that severely penalizes any effort to reach extreme speeds using chemical propulsion. With each small increase in velocity, the amount of fuel required doesn't merely rise, it explodes exponentially. The curve becomes so steep that it rapidly surpasses any amount of matter that could physically exist. Gravity assists ease this constraint slightly by allowing spacecraft to borrow energy from planets without burning additional fuel. By precisely timing close flybys of massive worlds, a spacecraft can trade momentum with a planet, slowly building speed through gravitational interactions. The Voyager probes relied heavily on this method, slingshotting from Jupiter to Saturn to gain the velocities that eventually carried them toward interstellar space. The Parker Solar Probe uses repeated flybys of Venus to build up its record-breaking speeds near the Sunday. The physics behind gravity assists involves falling toward a planet and accelerating as gravity pulls you in, then departing along a path that converts a small portion of the planet's orbital momentum into added spacecraft velocity. The planet gives up an almost immeasurable fraction of its orbital energy, while the spacecraft gains a meaningful increase in speed. After each Voyager encounter, Jupiter now moves ever so slightly more slowly around the Sun, though the effect is far too tiny to detect. Each flyby granted the spacecraft thousands of miles per hour, but gravity assists are not limitless. The solar system contains only a finite number of massive planets positioned in ways that allow useful acceleration. Jupiter is our most powerful gravity assist option, and even it can only provide so much energy per encounter. Every boost in speed comes at the cost of years spent traveling to the next planetary flyby. The same orbital mechanics that enable gravity assists also restrict the total amount of energy that can be extracted from the available planets. A spacecraft designed purely to maximize gravity assists, bouncing between planets over decades with carefully planned trajectories, might eventually reach speeds close to 150,000 miles per hour. That would be about 4 times the current speed of Voyager, achieved only after 10 years or more of meticulous maneuvering. Even so, this is still utterly insufficient for interstellar travel on human timescales, still demanding tens of thousands of years to reach even the nearest stars. The highest outbound velocity achieved mainly through gravity assists belongs to New Horizons, which passed Pluto in 2015 at roughly 36,000 miles per hour relative to the Sunday. After receiving a substantial boost from Jupiter in 2007, the spacecraft sped toward the outer solar system faster than any previous mission on an outbound trajectory. The images it sent back revealed Pluto as a surprisingly complex and beautiful world, featuring nitrogen glaciers and towering mountains made of water ice. Yet even at this remarkable speed, the journey to our closest stellar neighbor would still take more than 80,000 years. Ion propulsion offers modest improvements over chemical rockets by greatly increasing exhaust velocity. These systems function by ionizing a propellant, usually xenon gas, and accelerating the charged particles using electric fields. The ions leave the engine at speeds 10 to 20 times higher than chemical exhaust, making the conversion of propellant mass into spacecraft velocity far more efficient. The Dawn spacecraft employed ion propulsion to explore the asteroid belt, becoming the first mission to orbit 2 different celestial bodies beyond Earth. Its ion engines enabled maneuvers that would have been impossible for chemical rockets of comparable mass. The spacecraft could slowly reshape its orbit over months of continuous thrust, accomplishing trajectory changes that chemical engines simply could not achieve with the fuel available. However, ion engines generate thrust so small that their advantages vanish when rapid acceleration is required. Dawn's ion drive produced about 90 millinewtons of force. To visualize how little that is, place a single sheet of paper flat on your hand. The downward force from that sheet is roughly equivalent to the thrust of an ion engine. Applied continuously over many years, this tiny force can eventually build up significant speed, but reaching that speed demands patience, measured in decades, not the days or weeks associated with chemical rocket burns. Even if you had unlimited fuel and could operate continuously for an entire century, ion propulsion still falls far short of the speeds required for interstellar travel on human timescales. You could keep an ion engine running for a full human lifetime and never reach velocities that would significantly shorten the trip to even the nearest stars. This technology is exceptionally good at precise, efficient movement within our solar system, but it offers no real answer to the problem of interstellar distance. Ion drives are extraordinary at what they are designed to do, but what they can do simply is not sufficient. Nuclear thermal rockets sit one rung higher on the propulsion ladder. These engines function by channeling hydrogen propellant through a nuclear reactor, heating it to extreme temperatures before ejecting it through a nozzle. Because the heat comes from nuclear reactions rather than chemical burning, the hydrogen can be expelled at speeds roughly twice those achievable with chemical propulsion, effectively doubling exhaust velocity and easing the brutal constraints imposed by the rocket equation. During the 1960 seconds and early 1970 seconds, NASA thoroughly tested nuclear thermal rockets as part of the NERVA program. Engineers carried out dozens of successful reactor tests, operating nuclear engines for long durations and proving that nuclear thermal propulsion could work reliably. By 1973, the technology was sufficiently developed for real missions, but political priorities and budget limitations brought the program to an end. We have understood how to build nuclear rockets for more than 50 years and simply chose not to pursue them further. In theory, a nuclear thermal rocket could accelerate a spacecraft to around 100,000 miles per hour using reasonable fuel ratios. That speed is a substantial improvement over chemical rockets, roughly tripling what combustion alone can provide. At this velocity, a journey to Proxima Centauri would be shortened to about 28,000 years, still far beyond the lifespan of any human, still longer than the entirety of recorded human civilization, yet an improvement nonetheless. Solar sails may be the most graceful propulsion idea of all, using the pressure of sunlight itself to push a spacecraft forward without carrying any fuel at all. When photons strike a reflective surface, they transfer a tiny amount of momentum, nudging that surface in the direction the light is traveling. A very large, extremely lightweight reflective sheet could use this effect to slowly build up speed over time. In 2010, the Japanese Icarus spacecraft demonstrated this concept by deploying a 14-meter membrane and achieving measurable acceleration driven solely by sunlight. This mission showed that solar sailing works in reality, not just in theory. Light can move objects through space, and advanced sails could exploit this effect for propulsion without using a single gram of fuel. Near the sun, where radiation intensity is strongest, a solar sail could theoretically achieve acceleration approaching 1% of Earth's surface gravity. That may sound impressive until you realize that sustaining this acceleration requires remaining close to the sun, while the entire purpose of propulsion is to travel away from it. As a sail moves outward, the intensity of sunlight decreases with the square of the distance. Double your distance from the sun, and the radiation pressure drops to 1/4 of its previous value. What seems promising near the sun quickly fades in the outer solar system and becomes effectively non-existent in interstellar space. A solar sail launched from a close solar pass might eventually reach speeds of several 100,000 miles per hour before sunlight becomes too weak to provide meaningful acceleration. At 500,000 miles per hour, roughly 100 times Voyager's current speed and faster than any spacecraft humanity has ever flown, the trip to the nearest star would still take more than 5,000 years. Over the course of a human lifetime at that speed, you would travel about 350 billion miles, or roughly 0.6 light years. You could cover close to 1/7 of the distance to Proxima Centauri, an extraordinary achievement, yet you would still die in the emptiness between stars, never arriving at your goal. This is the harsh reality imposed by current and near-future propulsion technologies. The maximum speeds achievable by any system humanity has built, tested, or could realistically construct within the next century are not sufficient to carry a human being beyond our immediate cosmic neighborhood within a natural lifespan. Chemical rockets are fundamentally inadequate. Ion engines are far too weak. Nuclear thermal rockets improve matters, but nowhere near enough. Solar sails cannot accelerate large masses to the required velocities. We remain, for all practical purposes, confined to a region only a few light hours from our home planet. The psychological weight of this limitation shaped early scientific thinking about interstellar travel. Many physicists of the 20th century regarded journeys between stars as physically impossible for biological beings. The energy demands appeared overwhelming, and the travel times exceeded any reasonable definition of what could be considered practical. Cosmic radiation exposure over decades-long journeys would build up to doses that no human could survive. The immense, nearly empty gulfs separating stars seemed almost deliberately arranged to block life from traveling between one stellar system and another. Some researchers came to believe that the universe enforces a kind of cosmic quarantine, confining intelligent beings to their home planets through nothing more than sheer distance. The speed of light formed a boundary that no amount of inventive engineering could ever surpass. We might one day exchange messages with distant civilizations using radio waves that take years or even centuries to reach their destination, but visiting them would remain impossible. We would never clasp hands with an alien being, never set foot on a planet circling a different sun. Space itself appeared to forbid such journeys through the unforgiving mathematics of space and time. And yet, concealed within the very equations that seem to lock humanity in place, there exists a loophole so extraordinary that it reshapes everything we believe about distance, time, and the true limits of human exploration. This loophole was uncovered in 1905 by a 26-year-old patent clerk working in Bern, Switzerland. His name was Albert Einstein, and he posed a deceptively simple question that would overturn 3 centuries of assumptions about how the universe works. Einstein asked what would happen if you could travel alongside a beam of light. What would you observe? How would time flow? What would become of the space around you? The answers he arrived at ran counter to every instinct humans had developed about motion, time, and distance. They showed that the barrier confining humanity to our cosmic neighborhood is far less rigid than it seems. Distance and time, it turns out, are not the fixed, absolute quantities suggested by everyday experience. They are malleable. They can stretch and compress depending on how quickly you move through space. A clock aboard a rapidly moving spacecraft does not tick at the same pace as a clock left behind on Earth. A measuring rod carried by a fast-moving traveler does not retain the same length as an identical rod at rest. The universe manipulates space and time in ways that make the seemingly impossible suddenly attainable. To grasp how far a human could truly travel within a single lifetime, we must first let go of our intuitive ideas about motion. We have to step into a domain where clocks run at different speeds depending on their velocity, where distances shrink for travelers moving fast enough, and where the 80-year limit imposed by human mortality becomes far more flexible than it appears. The universe follows rules that seem almost purpose-built to frustrate our ambitions for cosmic exploration. Yet, embedded within those same rules are hidden clauses that could allow one human lifetime to span distances that today exist only in our most remote telescopic observations. The same laws of physics that establish the light-speed barrier also supply the means to render that barrier nearly meaningless for the travelers themselves. What follows will permanently change how you think about speed, time, and the ultimate boundaries of human exploration. The cosmic prison we appear confined within has a doorway, and physics itself provides the key. In 1905, a 26-year-old patent clerk in Bern, Switzerland, submitted a paper to the German physics journal Annalen der Physik. The article carried a modest title that gave no indication of its radical implications. On the electrodynamics of moving bodies contained no advanced mathematics beyond algebra. It cited almost no earlier scientific work. It was authored by someone with no university post, no laboratory, and no research funding. And yet this single paper would dismantle 3 centuries of beliefs about how the universe functions and demonstrate that time itself bends in response to motion. Albert Einstein began with an assumption so straightforward it seemed unremarkable. The speed of light in a vacuum is the same for every observer, no matter how fast that observer is moving. Whether you are standing still on Earth or racing through space at half the speed of light, you will always measure light, traveling at exactly 186,282 miles per second. This consistency is not a flaw in our instruments or a technological constraint. It is embedded in the fundamental fabric of reality. From this lone assumption, Einstein drew conclusions that shattered common sense. If the speed of light must remain identical for all observers, then something else has to change. That something, astonishingly, is time itself. Clocks aboard moving spacecraft tick more slowly than identical clocks that remain at rest. This phenomenon, known as time dilation, sounded almost nonsensical when it was first suggested. How could time, something we instinctively think of as constant and universal, pass at different rates simply because of how fast you are moving? Yet, the mathematics left no room for doubt, and within a few decades, experiments confirmed exactly what Einstein had deduced through pure reasoning. Time dilation is real, it can be measured, and it fundamentally reshapes our understanding of the boundaries of human exploration. The link between speed and time dilation is described by a strict mathematical relationship. Einstein introduced a quantity that physicists refer to as gamma, also called the Lorentz factor. This value tells you precisely how much time slows down at any particular velocity. To determine gamma, you take 1 and divide it by the square root of 1 minus your velocity squared divided by the speed of light squared. The equation may look daunting at first glance, but it produces numbers that ultimately decide the fate of interstellar travelers. At ordinary speeds encountered in daily life, gamma is almost indistinguishable from 1. A car moving at highway speed experiences time dilation so tiny that even the most sensitive atomic clocks struggle to detect it. Someone flying on an airplane might age a few nanoseconds less than a person who remained on the ground during a cross-country trip. The effect is real, but it has no meaningful impact on everyday life on Earth. The situation changes dramatically as velocity rises to a significant fraction of the speed of light. At 50% of light speed, gamma reaches 1.15. Time on board, the spacecraft runs about 15% slower than time on Earth. 1 year, experienced by the crew, corresponds to roughly 14 months passing back home. It is noticeable, but still not life-altering. At 90% of light speed, gamma increases to approximately 2.3. For every year that passes on the rapidly moving ship, 2 years and 4 months go by on Earth. A voyage lasting 50 years from the traveler's point of view would mean that 115 years had elapsed on Earth. The crew would return to discover their grandchildren grown old and their great-grandchildren shaping the world. Increase the speed to 99% of light speed and gamma climbs to 7.1, and the effect intensifies dramatically. For each year lived by the traveler, 7 years pass on Earth. 10 years aboard the ship corresponds to 70 years back home. A journey lasting 50 subjective years would span 355 years of Earth's history. You would leave behind one civilization and come back to find a completely different one in its place. At 99.9% of light speed, gamma rises above 22. In this regime, 22 years of Earth time are compressed into a single year on the spacecraft. The gap has become enormous. A 50-year journey would correspond to 1,100 years passing on Earth. The Roman Empire collapsed less than 1,600 years ago. A trip of this length would bridge eras comparable to the rise and fall of entire civilizations. The mathematics continue without mercy as velocity edges ever closer to light speed. At 99.99%, gamma exceeds 70. At 99.999%, gamma goes beyond 223. At 99.9999%, gamma climbs past 707. Each extra 9 added to the speed pushes the time dilation factor upward by roughly a factor of 3. These figures completely change how we think about traveling between stars. Now, imagine not a journey to the nearest star, but to something farther away. Vega, one of the brightest stars visible in our night sky, is located about 25 light-years from Earth. At conventional spacecraft speeds, reaching Vega would take hundreds of thousands of years. No human could survive even a fraction of that time. But at 99% of light speed, with gamma equal to 7.1, the situation is transformed. From Earth's frame of reference, the trip lasts about 25 years and 3 months. Light speed remains an absolute limit, and it cannot be surpassed. However, from the traveler's perspective, time dilation compresses that duration by a factor of 7. The subjective travel time drops to roughly 3.5 years. You could journey to Vega, spend time exploring any planets orbiting that brilliant blue-white star, and return to Earth having aged only 7 years, while 25 years passed at home. Increase the speed to 99.9% of light speed, and the numbers become even more astonishing. With gamma at 22, that same 25-year journey is reduced to just over 1 year of experience time. You could travel to Vega and come back before celebrating your 2nd birthday on board the ship. Earth would age 50 years during your round trip, while you would age only 2. The Pleiades star cluster, that well-known group of hot blue stars visible to the naked eye in winter skies, is located approximately 440 light-years from Earth. At ordinary speeds, reaching the Pleiades would take millions of years. At 99.99% of light speed, with gamma exceeding 70, the subjective travel time shrinks to around 6 years. A person could journey to one of the most renowned star clusters woven into human mythology, move between several stellar systems inside that cluster, and then return while having aged only about 15 years, even as Earth advanced by nearly 900 years. The core of our galaxy is located roughly 26,000 light-years from us. Hidden there is a black hole with a mass 4 million times greater than our Sun, surrounded by tightly packed star clusters and extreme, violent phenomena found nowhere else in the Milky Way. Traveling at 99.999% of the speed of light, with a gamma factor exceeding 223, the experienced travel time shrinks to about 116 years. That is still longer than a single human lifetime. But it falls within the reach of a multi-generational crew or explorers willing to rely on life extension technologies that may appear in future centuries. Increase the speed to 99.9999% of light speed, with gamma exceeding 700. And the journey to the galactic center becomes possible in roughly 37 years of ship time. A traveler could depart Earth at age 25, travel to the supermassive black hole at the heart of our galaxy, carry out observations that cannot be performed from Earth, and arrive having aged to 62. On returning, they would discover that more than 52,000 years had passed on Earth. Yet they themselves would have lived what feels like a normal human lifespan. The Andromeda Galaxy represents the ultimate challenge for relativistic travel within what we might describe as the local universe. At a distance of 2.5 million light-years, Andromeda is the nearest large galaxy to our own. Its trillion stars form a spiral structure larger than the Milky Way, potentially containing countless worlds and perhaps other civilizations. No conventional propulsion system could ever cross this gulf within any meaningful span of time. And yet, at speeds where gamma reaches 1 million, achievable only when velocity is so close to light speed that the distinction becomes almost philosophical, the experienced travel time to Andromeda falls to approximately 2.5 years. A traveler could pass through the vast emptiness between galaxies, explore an entirely separate island universe, and feel as though the journey lasted less time than a typical doctoral program. During that same interval, Earth would age by 2.5 million years. Human civilization would almost certainly be unrecognizable or long extinct upon their return. But the traveler would have aged only a few years. These calculations uncover a deep truth that Einstein encoded in his work but that everyday experience tends to hide. The universe has not been constructed with barriers meant to forbid cosmic exploration. Time dilation offers a pathway that could allow human consciousness to span distances that light itself needs millions of years to cross. The true limitation is not the laws of physics but engineering. The equations allow for interstellar and even intergalactic travel within a human lifetime. We simply do not yet possess the technology required to reach such extreme speeds. But why do these astonishing velocities demand such immense amounts of energy? The explanation lies in another of Einstein's revolutionary ideas, captured in the most famous equation in all of physics. E=mc² tells us that mass and energy are equivalent, interchangeable expressions of the same underlying reality. This equivalence has powerful consequences for anything attempting to move at relativistic speeds. As an object accelerates, it gains kinetic energy. At low velocities, this increase follows the familiar rules described by Isaac Newton centuries ago. If you double your velocity, your kinetic energy increases by a factor of 4. The relationship is simple and places no fundamental ceiling on speed, as long as sufficient fuel is available. However, as velocity approaches a significant fraction of the speed of light, something unexpected occurs. The energy required to continue accelerating begins rising far more quickly than Newton's equations would predict, dramatically so. The object starts to behave as if it has more mass than it originally did. This phenomenon, known as relativistic mass increase, becomes stronger as velocity climbs. At 50% of light speed, an object behaves as though it has about 15% more mass than it has at rest. The additional energy supplied to accelerate further seems to be absorbed into this increase in mass, instead of producing proportional gains in speed. By the time the object reaches 90% of light speed, its effective mass has more than doubled. The same engine thrust that once produced rapid acceleration now results in a sluggish response, as if the spacecraft had suddenly become enormously heavy. At 99% of the speed of light, an object's effective mass increases by a factor of 7. At 99.9%, that factor rises beyond 22. Every small step closer to light speed demands not merely additional energy, but exponentially greater amounts of it. This behavior follows the same gamma factor that governs time dilation, except here it works against the traveler rather than benefiting them. This increase in effective mass is the reason the speed of light stands as an absolute boundary for any object that has rest mass. As velocity draws nearer to light speed, effective mass trends toward infinity. Pushing an infinite mass to accelerate would require infinite energy. Because infinite energy cannot exist, the final approach to light speed becomes asymptotic. You can keep getting closer, stacking 9 after 9 onto your velocity when expressed as a percentage of light speed, yet you never truly arrive. Even well below this theoretical ceiling, the real energy demands of relativistic travel are astonishing. Imagine accelerating a small probe with a mass of perhaps 1,000 kilograms to 90% of the speed of light. The kinetic energy required surpasses 10 to the 19th joules. Written out in full, this value contains 20 digits. It corresponds to roughly 2 seconds of the sun's total energy output, or about 1 million years of humanity's entire energy consumption, all focused into pushing a single modest spacecraft to that speed. For a crude vehicle designed to support human life on an interstellar voyage, the mass could easily reach 100,000 kilograms or more. The energy requirement increases in direct proportion. Accelerating such a ship to 90% of light speed would demand energy comparable to several minutes of the sun's total output. This is not a technological hurdle waiting to be solved with better engineering. It is a fundamental demand enforced by the structure of spacetime itself. The energy cost becomes even more severe when you remember that travelers usually want to slow down upon arrival. Decelerating from 90% of light speed consumes exactly the same amount of energy as accelerating to that speed in the first place. A round trip doubles the requirement once again. A journey to Vega and back at 90% of light speed would therefore need 4 times the energy required for a one-way acceleration, exceeding the sun's total output for about a quarter of an hour. These enormous requirements explain why relativistic travel remains a theoretical concept, even though the underlying physics has been understood for more than a century. No propulsion system humanity has ever constructed, tested, or seriously proposed can supply energy on these scales. Chemical rockets fall short by factors of billions. Nuclear fission offers improvement but remains profoundly insufficient. Even nuclear fusion, the same process that powers the sun, struggles to deliver the energy density needed for practical relativistic propulsion. The acceleration profile itself adds further limitations. Humans can tolerate continuous acceleration at 1 Earth gravity indefinitely. It feels like normal weight, allowing travelers to walk, eat, sleep, and function normally throughout the journey. Higher levels of acceleration quickly become problematic. Sustained acceleration at 2 gravities leads to fatigue and health issues. 5 gravities can cause loss of consciousness. 10 gravities can be fatal. With continuous acceleration at 1 gravity, a spacecraft would reach 90% of light speed in about 11 months. During the first half of this phase, you accelerate toward your destination while steadily increasing speed. At the midpoint of the journey, the spacecraft would rotate and begin decelerating at 1 gravity, arriving at the destination with 0 relative velocity after the same length of braking time. This constant acceleration approach fundamentally alters travel time calculations. Instead of rapidly reaching a high speed and then coasting, the entire journey is spent either accelerating or slowing down. For shorter trips, this strategy actually requires more energy than including a coasting phase would. For extremely long journeys, however, continuous acceleration reduces travel time by maintaining thrust throughout the voyage instead of drifting at a constant velocity. 1 year of acceleration at 1 Earth gravity would bring a spacecraft to roughly 77% of light speed. 2 years would reach about 97%. 3 years would push beyond 99%. As light speed is approached, velocity gains diminish, with each additional year of acceleration adding smaller increases. Yet, time dilation compensates for this slowdown, compressing the traveler's subjective experience of the journey, even as acceleration becomes less efficient. The twin paradox arises naturally from these relativistic effects and merits close attention because it demonstrates just how profoundly time dilation can shape human experience. Consider the following thought experiment. Imagine 2 identical twins, Alice and Bob. Alice steps aboard a spacecraft capable of relativistic travel and sets off toward a star located 20 light-years away, moving at 90% of the speed of light. Bob stays behind on Earth. From Bob's viewpoint on Earth, Alice's outward journey lasts about 22 years, and her return trip requires another 22 years. Bob therefore ages 44 years as he waits for his twin to come back, passing from young adulthood all the way to retirement age during Alice's absence. From Alice's point of view inside the spacecraft, the passage of time is very different. Because of time dilation, each leg of the journey is compressed. At 90% of light speed, the gamma factor is approximately 2.3. What Bob measures as a 22-year outbound trip feels to Alice like only about 9.5 years. The return leg feels like another 9.5 years. In total, Alice experiences just 19 years of travel, while Bob experiences 44. When Alice finally returns to Earth, she is 19 years older than when she departed, while Bob is 44 years older. The twins, born on the same day, are now separated by 25 years in biological age. Alice's hair might only be showing the first traces of grey, while Bob's has turned completely white. Alice may still be actively building her career, while Bob is already thinking seriously about retirement. This situation deeply unsettled early critics of relativity, who pointed out that motion itself is relative. From Alice's perspective, it was Bob who moved away and later came back. Why, then, should Alice be the one who ages less instead of Bob? The answer lies in the crucial asymmetry between their experiences. Alice undergoes acceleration when her spacecraft changes speed and direction, while Bob remains in an inertial frame and experiences no acceleration at all. This difference breaks the symmetry between their reference frames and determines who ages less. The so-called twin paradox has been confirmed experimentally using highly accurate atomic clocks. In 1971, physicists Joseph Hafele and Richard Keating flew cesium atomic clocks around the world aboard commercial airliners and compared them with identical clocks that stayed on the ground. The clocks that traveled gained about 270 nanoseconds relative to the stationary clocks, exactly as special relativity predicted. The effect was extremely small because airplane speeds are tiny compared to the speed of light, but it was real, measurable, and it confirmed predictions Einstein had made a century earlier. Time dilation opens up unusual possibilities for relativistic travelers beyond differences in aging. Signals from Earth could reach travelers during their journey, allowing them to receive news, entertainment, and personal messages from home. However, this information would arrive compressed in time, with years of Earth's broadcasts packed into months of ship time. Travelers could watch decades of Earth's history unfold during their voyage, seeing children grow into adults and adults grow old in accelerated playback. Communication in the opposite direction presents different difficulties. Messages sent from the spacecraft would take years to reach Earth, and replies from Earth would take years to return. A traveler moving at 99% of the speed of light toward a star 100 light-years away would experience the journey as lasting roughly 14 years, but a message sent from the ship just 1 year into the trip would require decades to reach Earth, and Earth's response would not arrive until long after the traveler had already reached the destination. The visual experience of traveling at relativistic speeds would be just as strange. Light coming from ahead of the spacecraft becomes blue-shifted, with its frequency increased by the Doppler effect caused by the ship's motion toward the source. Stars in front would shift from their familiar colors toward blue, then into ultraviolet, and eventually into X-ray frequencies as the velocity increased. Constellations that once guided navigation would turn into sources of invisible radiation, detectable only with specialized instruments. Light arriving from behind the spacecraft undergoes the opposite transformation. Stars to the rear become red-shifted, their light stretched to longer wavelengths. They fade from visible colors into infrared, then into radio waves, and eventually become undetectable as their radiation drops below the sensitivity of any instrument. Relativistic aberration further warps the traveler's view of the universe. Light arriving from the sides of the spacecraft appears to be pushed forward, squeezed into a narrowing cone in the direction of motion. At 90% of the speed of light, this effect concentrates most of the visible universe into a region about 60 degrees wide, directly ahead of the spacecraft. At 99% of light speed, this region contracts to roughly 16 degrees. At even greater velocities, the entire cosmos collapses into a single brilliant point of light straight ahead, leaving complete darkness behind. The interstellar medium also poses dangers that intensify as velocity increases. The space between stars is not completely empty. On average, each cubic centimeter contains about one hydrogen atom, along with small amounts of helium, heavier elements, and dust grains. At low speeds, this material presents no danger. Spacecraft move through it much like bullets slicing through air, scarcely aware that it is even there. But once velocities approach relativistic regimes, this thin material turns into a lethal radiation field. Every hydrogen atom collides with the spacecraft, carrying kinetic energy that scales with the square of the gamma factor. At 90% of light speed, a single hydrogen atom impact releases energy on par with that of a cosmic ray particle. At 99% of light speed, that energy rises by an additional factor of 20. The forward-facing surfaces of the spacecraft would endure an unrelenting storm of high-energy particles capable of harming electronic systems, wearing down structural materials, and penetrating biological tissue. Protecting against this radiation demands either extremely heavy physical shielding or active deflection mechanisms. Strong magnetic fields might be used to sweep charged particles away from the spacecraft, but the required field strengths increase sharply as velocity rises. Adding physical shielding increases mass, and that added mass must itself be accelerated to relativistic speeds, further amplifying the already immense energy demands. In spite of these daunting obstacles, the physics underlying relativistic travel is well established and thoroughly tested. Time dilation is not a speculative idea or a mathematical trick. It is a measured effect, confirmed through decades of high-precision experiments. The equations themselves allow for human journeys across interstellar, and even intergalactic, distances within a single biological lifetime. The true obstacle is not the laws of physics, but propulsion capability. This raises an unavoidable question. What forms of technology could realistically reach the speeds needed to take advantage of time dilation? What kinds of engines could supply the staggering energy requirements that relativistic travel demands? The next stage of this discussion turns to propulsion ideas that might convert these mathematical allowances into practical engineering systems, ranging from nuclear detonations to antimatter reactions to beams of light driving ultra-thin sails across the universe. The divide between the velocities of today's spacecraft and the speeds required for interstellar travel within a human lifetime is almost impossible to grasp. Our fastest probes drift through space at about 1/10,000th of the speed of light. Significant time dilation effects only begin to appear above 10% of light speed, and they become truly dramatic only beyond 90%. Bridging this enormous velocity gap requires propulsion concepts that go far beyond anything humanity has so far built, tested, or even fully designed. To understand the scale of the challenge, consider a concrete example. The Parker Solar Probe reaches roughly 0.06% of light speed during its closest passes by the Sun. Achieving 10% of light speed, the point at which relativistic effects become noticeable, would mean increasing velocity by a factor of about 170. Reaching 90% of light speed, where time dilation drastically shortens travel times, would require a velocity increase roughly 1,500 times greater than our current maximum. This is not a small step forward in engineering. It represents a fundamental transformation in propulsion technology, one that spans 6 orders of magnitude. Even so, humanity has already imagined propulsion concepts that might one day cross this vast gulf. Some rely only on further engineering development grounded in well-understood physics. Others would require major breakthroughs in materials science, energy generation, or fundamental engineering methods. A few venture into more speculative territory, where even the underlying physics is not yet fully resolved. Exploring these ideas reveals both the extraordinary potential and the profound constraints involved in achieving interstellar travel within human lifetimes. Among these concepts, nuclear pulse propulsion stands out as one of the most radical propulsion systems ever seriously examined by mainstream engineers. The idea took shape in the late 19 at the General Atomics Laboratory in San Diego, where a group of exceptionally creative physicists posed a question that sounded outrageous at first glance. What if nuclear explosions themselves could be used to propel a spacecraft? What if, instead of carefully containing nuclear energy inside a reactor, you detonated nuclear devices behind a vehicle and used the resulting blast waves to push it toward the stars? This proposal, later known as Project Orion, drew the attention of some of the leading scientific minds of the time. Freeman Dyson, Theodore Taylor, and many other physicists and engineers spent years turning this seemingly absurd notion into detailed and quantitative engineering designs. They were not indulging in fantasy. They approached the idea with seriousness, performing careful calculations and even conducting real-world experiments. The core concept behind Orion is surprisingly straightforward. The spacecraft would carry a large stockpile of nuclear explosive devices, essentially specially engineered bombs. These devices would be released one by one from the rear of the spacecraft and detonated at precisely calculated distances. Each explosion produces a rapidly expanding plasma fireball that spreads outward in all directions. A massive pusher plate mounted at the back of the spacecraft intercepts a portion of this plasma, absorbing its momentum and converting it into forward motion, steadily driving the vehicle ahead. Shock absorbers positioned between the pusher plate and the crew module are designed to soften the brutal shocks, transforming violent impulses into levels of acceleration that humans could endure. The engineers behind Project Orion carried out real-world experiments using conventional chemical explosives instead of nuclear devices. They constructed small-scale models fitted with pusher plates and set off explosive charges beneath them, proving that the idea functioned outside of theory. These models successfully lifted off. The pusher plates withstood repeated detonations. The shock absorption systems functioned as intended. International nuclear test ban treaties brought the program to an end in 1963 before full atomic detonations could be tested, but by that point the underlying physics had already been confirmed. Detailed calculations indicated that Orion could reach performance levels far beyond any propulsion system imagined at the time or built since. A relatively small Orion craft powered by fission bombs could attain speeds of 3 to 4% of the speed of light. Larger versions using hydrogen fusion bombs might potentially reach 8 to 10% of light speed. The most ambitious concepts, demanding engineering far beyond what was possible in the 1,960 seconds, could perhaps approach 15% of light speed or more. At 10% of light speed, a voyage to Tau Ceti, a sun-like star located about 12 light-years away and thought to possibly host habitable planets, would take approximately 120 years. That is still longer than a single human lifespan. But it falls within the realm of multi-generational expeditions or for travelers prepared to spend most of their lives in transit. Time dilation at this speed offers little advantage, shortening the trip by only around 0.5%, meaning the spacecraft would experience nearly the same duration that observers on Earth would measure. The engineering obstacles facing nuclear pulse propulsion are severe, but not impossible to overcome. The pusher plate must endure repeated exposure to nuclear fireballs, with temperatures reaching millions of degrees, arriving in microsecond bursts thousands of times over the course of the journey. Materials science has progressed dramatically since the 1,960 seconds, and modern composites along with refractory metals could plausibly satisfy these extreme demands. The shock absorption system must reliably convert immense, sudden forces into steady acceleration without tearing the vehicle apart or harming its crew. With enough engineering effort, this challenge appears solvable. Transporting thousands of nuclear devices introduces obvious risks, both during launch and throughout the mission. A catastrophic failure during departure from Earth could disperse radioactive material across vast regions. A serious malfunction during flight could end the mission entirely. Even so, nuclear pulse propulsion relies on no new laws of physics and requires no materials or technologies beyond what humanity is capable of developing. It stands as the most near-term route to interstellar speeds, using principles we already understand. A later investigation known as Project Longshot carried out by the United States Naval Academy in 1987 and 1988, explored a fusion-powered version of nuclear pulse propulsion. This concept proposed using small fusion explosions instead of fission bombs, improving efficiency and significantly reducing radioactive risk. Longshot was designed to travel to Barnard's star, roughly 6 light-years away, in about 100 years at close to 4.5% of light speed. The study concluded that such a mission was technically achievable with technology that could be developed within a few decades. Antimatter propulsion occupies a distinctive place among interstellar propulsion ideas, offering an energy density that surpasses all other known fuels while remaining firmly rooted in well-established physics. When a particle of matter encounters its antimatter counterpart, both are completely annihilated, converting 100% of their combined mass directly into energy. By comparison, nuclear fission converts only about 0.1% of mass into energy, while nuclear fusion achieves roughly 0.7%. Antimatter is about 140 times more energy dense than fusion, and 1,000 times more energy dense and efficient than fission. Just 1 gram of antimatter, annihilating with 1 gram of ordinary matter, releases around 180 trillion joules of energy. This is equivalent to the explosive power of the Hiroshima atomic bomb. It also matches the energy consumption of an average American household over 4.5 years. Such energy could propel a small spacecraft to speeds that chemical rockets could never reach, no matter how much fuel they carried. The immense energy density of antimatter makes it, in theory, an ideal candidate for closing the gap to relativistic velocities. An antimatter rocket would operate by channeling the products of matter-antimatter annihilation through a magnetic nozzle to produce thrust. When an electron encounters a positron, its antimatter equivalent, both disappear and generate gamma rays. When a proton meets an antiproton, the annihilation produces a cascade of particles known as pions, which can be guided magnetically to generate propulsion. These pions then break down into lighter particles, including muons, which can themselves be guided using magnetic fields before they decay further into electrons and neutrinos. The exhaust velocity produced by an antimatter rocket approaches a substantial fraction of the speed of light, far surpassing what any chemical, nuclear, or fusion-based propulsion system could ever deliver. This extraordinarily high exhaust velocity fundamentally reshapes the rocket equation that so harshly constrains chemical propulsion. With antimatter, reaching relativistic spacecraft speeds becomes a matter of mathematics rather than an absurd requirement for more fuel than exists within the observable universe. Imagine a voyage to Epsilon Eridani, a young sun-like star located roughly 10.5 light-years from Earth and known to host at least one confirmed planet, traveling at 30% of light speed, a velocity that could be achieved using approximately 100 km of antimatter for a relatively modest probe. Such a journey would take around 35 years as measured from Earth. Because of time dilation at this speed, the experience of the traveler would be shortened to about 33 years, a small but still meaningful reduction. A human could leave Earth at the age of 30 and arrive at Epsilon Eridani with a subjective age of 63, potentially still healthy and energetic enough to carry out meaningful exploration. Increasing the available antimatter supply allows for even higher velocities, along with far more dramatic benefits from time dilation. With several thousand kilograms of antimatter, a crewed spacecraft could theoretically be accelerated to 70 or 80% of light speed. At those speeds, the journey to Epsilon Eridani would still take approximately 13 to 14 years from Earth's point of view, but the traveler would experience only 8 or 9 years in total. What once appeared to consume nearly an entire human lifetime becomes instead a long yet manageable expedition. The seemingly insurmountable barrier facing antimatter propulsion is not rooted in physics, but in production. Antimatter does not naturally exist in meaningful quantities anywhere in the known universe. Every antiproton, intended for propulsion, must be created artificially through collisions inside particle accelerators, processes that demand enormous amounts of energy. Current worldwide antimatter production is estimated at only about 10 to 20 nanograms per year, generated mainly at facilities such as CERN in Switzerland and Fermilab in the United States. To grasp just how tiny this output truly is, consider that accumulating 100 kilograms of antimatter for a journey to Epsilon Eridani would require collecting today's global production for roughly 5 billion years. The energy cost worsens the situation dramatically. Producing antimatter through particle collisions consumes roughly 10 billion times more energy than the antimatter ultimately contains. Creating enough antimatter for even a single interstellar probe would demand energy expenditures greater than the total power consumption of human civilization sustained over centuries or even millennia. Storing antimatter presents challenges that are just as severe. Antimatter annihilates instantly when it comes into contact with normal matter, which means it must be held in perfect vacuum using precisely controlled magnetic fields. The fuel must never touch the walls of its container, must remain stable through the intense vibrations of launch, and must survive storage periods lasting decades during interstellar travel. The longest duration for which antimatter has ever been successfully stored is approximately 16 hours, an achievement reached at CERN in 2023. Extending this from 16 hours to many decades would require an improvement factor of roughly 10,000. These combined production and storage obstacles push antimatter propulsion far into the distant future, assuming it ever becomes practical at all. The physics itself is elegant and compelling. The engineering, however, lies far beyond any capability we can realistically foresee. Antimatter serves as a theoretical ideal, a benchmark against which other propulsion ideas can be compared, rather than a near-term route to the stars. Beamed energy propulsion offers a way around the core problem that affects every rocket-based concept. Conventional rockets must carry their energy source with them, and that energy source has mass that must also be accelerated. This creates a relentless feedback loop in which adding fuel to increase speed also adds mass, which then requires even more fuel to accelerate. Beamed energy systems break this loop by keeping the power source at its point of origin. The idea dates back to the 1960 seconds when physicist Robert Forward proposed using extremely powerful lasers to push lightweight solar sails to interstellar speeds. A sail carries no onboard fuel at all. Instead, it accelerates by reflecting photons, gaining momentum directly from light. With lasers of sufficient power and sails that are light enough, velocities approaching significant fractions of light speed become theoretically possible. Breakthrough Starshot, announced in 2016 with $100 million in initial funding from Russian billionaire Yuri Milner, stands as the most serious modern attempt to turn beamed energy propulsion from theory into reality. The initiative, which received support from the late Stephen Hawking prior to his passing, suggests employing a ground-based laser system to propel extremely small spacecraft, known as starships, to 20% of light speed. At such a velocity, reaching the Alpha Centauri system would take around 20 years. The Starshot breakthrough concept imagines a phased laser array with a combined power output nearing 100 gigawatts, roughly comparable to the electricity produced by 100 large nuclear power stations. This system would concentrate its energy on a spacecraft weighing just a few grams, made up of a highly reflective sail, perhaps 4 meters in diameter, attached to a miniature chip equipped with cameras, communication, hardware, and navigation systems. The immense pressure exerted by photons would drive this delicate craft from rest to 20% of light speed in about 10 minutes. The technical obstacles involved are immense, yet they may not be impossible to overcome. The laser array would need to hold a precise and coherent focus on a target that is accelerating at extraordinary rates, eventually moving so far away that the delay caused by light speed between the laser and the spacecraft grows from seconds to minutes. The sail itself would have to endure radiation levels intense enough to vaporize ordinary materials, demanding advanced reflective coatings that, for now, remain largely theoretical. Meanwhile, the tiny star chip would still need to house functional scientific instruments, despite having a mass smaller than that of a typical paperclip. Even so, the Starshot breakthrough presents clear benefits when compared with other interstellar approaches. Because the laser array stays on Earth, it can draw power from terrestrial energy sources, be serviced and upgraded over time, and reused for many missions. Each individual starship would be relatively inexpensive compared with traditional spacecraft, making it possible to launch hundreds or even thousands of them. This greatly increases the likelihood that at least some would survive the journey and transmit valuable data back home. The critical weakness of beamed energy propulsion for carrying humans, however, lies in the problem of slowing down. A sail pushed by a laser gains speed by reflecting light from behind, but it cannot decelerate in the same way because there is no laser waiting at the destination to provide an opposing force. A Starshot probe would therefore race through the Alpha Centauri system at 20% of light speed, with only a few minutes to make observations before it vanished into deep space forever. For robotic missions aimed at taking images, this might be acceptable. For human explorers who want to stop and investigate, this method is entirely inadequate. Magnetic sails present one possible answer to the deceleration challenge. A superconducting loop can generate an enormous magnetic field that interacts with charged particles in the interstellar medium or with the stellar wind near the destination star. This interaction produces drag that can gradually slow a spacecraft. In principle, a magnetic sail could reduce a vessel's speed from relativistic values to rest over periods lasting months or years. While the basic physics behind magnetic sail deceleration is sound, the engineering demands become extreme at higher speeds. Reducing velocity from 20% of light speed means shedding vast amounts of kinetic energy, which would heat the magnetic sail and nearby structures. The superconducting loops would need to retain their properties despite this heating, requiring highly advanced thermal control systems. In addition, the density of the interstellar medium varies significantly depending on the route taken, making deceleration behavior difficult to predict and manage with precision. Fusion propulsion may represent the most plausible route to achieving speeds where time dilation becomes significant for human travelers. Fusion reactions merge light atomic nuclei, most often hydrogen isotopes, releasing energy far greater than that produced by chemical reactions or nuclear fission. The Sun itself operates as a fusion reactor, turning hydrogen into helium and emitting the energy that sustains life on Earth. Applying this same process to propulsion could, in theory, open the stars to human journeys. The underlying physics of fusion propulsion is well established. When deuterium and tritium nuclei fuse, they form helium and a high-energy neutron, releasing about 17.6 million electron volts of energy. This is enormously greater than the few electron volts yielded by chemical reactions. A fusion-powered rocket could, in theory, achieve exhaust velocities of 3 to 5% of light speed, allowing spacecraft to accelerate to 10 or 15% of light speed with manageable fuel requirements. Project Daedalus, carried out by the British Interplanetary Society between 1973 and 1978, produced the most comprehensive engineering analysis of a fusion-driven interstellar probe. The proposed design featured a two-stage spacecraft that would burn pellets of deuterium and helium-3 using inertial confinement fusion. Intense electron beams would compress the fuel pellets until ignition occurred, and the resulting fusion products would be expelled through a magnetic nozzle to generate thrust. Daedalus was conceived as a vehicle capable of reaching Barnard's star, located at a distance of roughly 6 light-years, in about 50 years while cruising at 12% of the speed of light. Its first stage was designed to operate for 2 years, pushing the spacecraft up to 7.1% of light speed before being discarded. After separation, the second stage would continue firing for an additional 1.8 years, bringing the craft to its maximum velocity before it entered a long coasting phase toward its target. By any measure, the spacecraft would have been immense, with a launch mass of approximately 54,000 tons, most of that mass consisting of fuel. No system for slowing down was included in the design. Instead, the probe would rush through the Barnard star system at 12% of light speed, collecting data during a fleeting encounter. Once past the system, it would continue onward into interstellar space indefinitely. Its scientific objectives would be completed in just the few days it took to cross the target system. Project Icarus, launched in 2009 by the British Interplanetary Society together with the Tau Zero Foundation, returned to the Daedalus idea using more modern assumptions in physics and engineering. Studies under Icarus examined a range of fusion fuel options and engine designs, largely reinforcing the conclusion that speeds between 10 and 20% of light speed could be achievable with fusion propulsion, using technology that might realistically emerge within the next century. At 15% of light speed, a voyage to Sirius, the brightest star visible in Earth's night sky and located 8.6 light-years away, would take around 57 years as measured from Earth. At this speed, time dilation reduces the traveler's experience duration by only about 1%, offering almost no practical advantage. A person leaving Earth at the age of 25 would reach Sirius at about 82, having spent nearly their entire adult life en route. This scenario represents survival, but it falls far short of what could be considered practical interstellar travel. Achieving velocities where time dilation meaningfully benefits travelers would demand propulsion breakthroughs that go well beyond standard fusion concepts. One such idea was the Bussard ramjet, proposed in 1960 by physicist Robert Bussard, which presented an elegant theoretical alternative. Rather than carrying its own fusion fuel, the ramjet would collect hydrogen from the interstellar medium using vast magnetic fields, then fuse that material to generate steady thrust. In theory, a Bussard ramjet could accelerate continuously, gathering fuel as it moved and limited only by the relativistic increase in mass as it neared light speed. This concept fueled decades of science fiction and serious academic investigation. It appeared to promise genuine relativistic travel without the overwhelming fuel mass that constrains conventional rockets. However, detailed analyses eventually exposed fundamental flaws in the idea. On average, the interstellar medium contains about 1 hydrogen atom per cubic centimeter, with densities varying widely between regions. To gather enough hydrogen to sustain fusion, a magnetic scoop thousands of kilometers wide would be required. Yet this enormous structure would interact with the charged particles it captured, producing drag forces greater than the thrust the fusion reactions could supply. In effect, the ramjet would deploy a parachute far larger than its engine could overcome. More recent studies suggest the concept might function in exceptionally dense regions of space, such as inside giant molecular clouds, but it fails under typical interstellar conditions. With current understanding of physics, the vision of unlimited relativistic acceleration through fuel harvesting appears unattainable. Hybrid propulsion strategies, combining several technologies, may offer better performance than relying on a single method. A spacecraft could, for example, use nuclear pulse propulsion to gain initial speed, then employ a magnetic sail to slow down upon arrival. Alternatively, a laser-boosted sail might provide early acceleration, while an onboard fusion system handles deceleration and maneuvering near the destination. Imagine a hybrid mission to the Tau Cetus system, located 12 light-years away and believed to host multiple planet candidates, including worlds that may be habitable. The journey would begin with acceleration from a ground-based laser array, pushing against a sail attached to a fusion-powered spacecraft. During the first weeks, the laser would drive the craft up to 15% of light speed. The vessel would then coast for roughly 80 years before activating its fusion engine to slow down, arriving in the Tau Cetus system with enough reduction in velocity to enter orbit around the target star. This hybrid method minimizes the fuel mass required on board by outsourcing acceleration while preserving internal propulsion for deceleration, allowing genuine exploration rather than a brief fly-through. Even so, a total travel time of about 80 years still exceeds a typical human lifespan, though a crew departing in their 20s might survive to witness arrival in their hundreds. If we suppose that medical progress significantly extends the human lifespan over the next century, attention naturally turns to more speculative propulsion ideas that reach into areas of physics that are still theoretical or even entirely hypothetical. One such idea is the Alcubierre warp drive, introduced in 1994 by Mexican physicist Miguel Alcubierre, which outlines a configuration of space-time that could allow effective faster-than-light travel without violating special relativity. The basic idea involves compressing space in front of a spacecraft while expanding space behind it, forming a bubble of flat spacetime that rides along a distortion in the fabric of reality. Inside this warp bubble, the spacecraft itself remains stationary relative to its local spacetime environment. No speed limit is broken because the craft is not actually moving through space. Instead, spacetime is being reshaped to transport the vessel forward. In principle, destinations that light would take years to reach could be accessed in arbitrarily short durations, depending on the intensity of the spacetime distortion. The mathematical framework of the Alcubierre drive fits within general relativity. Its equations describe a configuration of spacetime that is internally consistent, though highly exotic. However, producing such a configuration demands negative energy density, a property that may not exist anywhere in nature. Even the most optimistic estimates indicate that the required energy would exceed the mass energy of Jupiter. More conservative and realistic calculations push this requirement far beyond the mass energy of the entire observable universe. As a result, the Alcubierre drive remains an elegant mathematical construct, with no identifiable route toward physical realization. Wormholes offer another speculative route for interstellar travel, one that could potentially bypass the velocity limitation altogether. These hypothetical structures, allowed by general relativity, would link distant regions of spacetime through shortcuts that exist outside ordinary three-dimensional space. A traveler entering one mouth of a wormhole could emerge from the other mouth, light-years, or even billions of light-years away, having effectively crossed no distance within the wormhole itself. For wormholes to be stable and traversable, they would require exotic matter with negative energy density to prevent gravitational collapse. Whether such exotic matter can exist is still unknown. Some calculations in quantum field theory suggest that small quantities of negative energy density might arise through quantum effects, but whether these effects could be amplified enough to stabilize a macroscopic wormhole remains entirely speculative. Even if wormholes could be created and maintained, their practical use introduces further complications. The mouths of a wormhole would still need to be positioned at the intended destinations. If one mouth must first travel to Tau Ceti at conventional speeds before forming a shortcut back to Earth, then the initial journey still demands solutions to the propulsion challenges that wormholes were meant to avoid. Returning to propulsion concepts rooted in well-established physics, the most realistic near-term frontier for interstellar travel likely involves advanced fusion-based systems, possibly enhanced by externally beamed energy for initial acceleration. With sustained research and development, such technologies could plausibly reach velocities of 15 to 20% of light speed within the coming century. At 20% of light speed, time dilation effects are modest but detectable. The gamma factor at this speed is approximately 1.021, meaning that 50 years of Earth time would correspond to about 49 years experienced aboard the spacecraft. Over a 50-year journey, the traveler gains roughly 1 year, noticeable but far from transformative in terms of the overall experience of interstellar travel. Achieving speeds where time dilation becomes dramatic, above 50% of light speed and ideally beyond 90%, would require propulsion breakthroughs that cannot currently be formulated even in theory. The gap between 20% and 90% of light speed may represent the greatest obstacle in all of propulsion physics. No known technology can cross this divide using any plausible fuel or energy source. Still, the laws of physics themselves do not forbid relativistic travel. The equations allow velocities arbitrarily close to the speed of light, constrained only by the energy available for acceleration. Time dilation truly does shorten journey times for those in transit, turning cosmic distances from utterly impossible into merely daunting. The universe has not placed absolute barriers in the way of interstellar exploration. It has simply set the cost extraordinarily high. Whether humanity will ever develop propulsion systems capable of reaching deeply relativistic speeds remains an open question. The engineering challenges are vast, and the energy demands exceed our current capabilities by factors that strain the imagination. The timescales involved in development extend across multiple generations, requiring a level of long-term dedication that human societies rarely sustain. Yet the underlying physics remains sound. The mathematical framework is unambiguous. With enough speed, a single human lifetime could, in principle, cover distances that light itself needs thousands or even millions of years to cross. The final section explores what unfolds when we assume propulsion has reached perfection, when we stop asking what speeds technology might realistically achieve, and instead ask what distances the laws of physics actually allow a human life to span. What emerges from this question exposes both the greatest possibilities and the absolute boundaries of human exploration in an ever-expanding universe. Now picture a civilization so advanced that propulsion technology is effectively flawless. Energy supplies are limitless. Acceleration to any chosen velocity happens instantly. At the press of a button, the engineering obstacles that dominate our current efforts have been overcome so completely that spacecraft routinely reach 99,999% of light speed. In that scenario, what becomes the true limit on how far a human could travel within a single lifetime? The answer does not come from technological shortcomings, but from the architecture of the universe itself. Even with propulsion that seems almost divine, the geometry of the cosmos enforces limits that no level of technology can surpass. These limits are embedded in the fabric of space, time, written into the expansion of the universe, and dictated by the finite age of everything that exists. They define the maximum possible reach of any traveler, regardless of speed, lifespan, or the sophistication of their civilization. Grasping these ultimate boundaries requires facing the true scale of cosmic distances and the strange behavior of space on the largest scales. The universe is not a fixed stage through which travelers simply move. It is a living, dynamic system that stretches and grows, pulling galaxies apart like raisins embedded in rising bread dough. This expansion generates horizons that no traveler can ever cross, no matter how fast they go or how long they live. The observable universe gives us the first crucial reference point for understanding these cosmic limits. This region, centered on Earth and extending roughly 46.5 billion light-years in every direction, includes every photon that has had time to reach our planet since the beginning of cosmic history. Its full diameter measures about 93 billion light-years. Within this vast volume lie approximately 2 trillion galaxies, each containing hundreds of billions of stars, each potentially hosting planets where life could have arisen and evolved. At first glance, this observable region appears to define the maximum possible range for exploration. Nothing beyond this boundary has ever been detected by any instrument humanity has constructed. No telescope, no radio receiver, no gravitational wave observatory has ever captured a signal from beyond the observable horizon. In a very real sense, this sphere represents the total extent of the universe accessible to human knowledge. Yet, the observable universe is not the same as the reachable universe, and this distinction is critically important for anyone imagining journeys across cosmic distances. The light we observe today from the most distant visible galaxies began its journey more than 13 billion years ago, when the universe was far younger and much smaller. During that immense travel time, cosmic expansion stretched the space between those galaxies and Earth. Objects that emitted light 13 billion years ago now lie about 46 billion light-years away, carried outward by the expansion of space itself. This expansion is still ongoing today. And more unsettling still, it is accelerating. In 1998, 2 independent research teams studying distant supernovae discovered that the expansion rate of the universe is increasing over time. This acceleration, driven by a mysterious component known as dark energy, which makes up approximately 68% of the universe's total energy content, means that distant galaxies move away from us faster with every passing year. This discovery, which earned the 2011 Nobel Prize in Physics, fundamentally changed our understanding of the universe's destiny. The influence of dark energy creates a boundary even more fundamental than the observable horizon. The Hubble sphere defines the distance at which the rate of cosmic expansion equals the speed of light. Objects located at this boundary, roughly 14 billion light-years from Earth, recede from us at exactly 186. 0.000 miles per second. Their recession speed matches the cosmic speed limit precisely, forming a threshold with deep consequences. Beyond the Hubble sphere, galaxies move away from us faster than light. This does not violate special relativity, because the galaxies themselves are not traveling through space at superluminal speeds. Instead, space itself is expanding, carrying the galaxies along like boats drifting on a swelling ocean. The distinction is essential, but it offers little reassurance to any would-be traveler, whether they are carried along by the stretching of space itself or moving through it. Objects located beyond the Hubble sphere move away faster than any signal or spacecraft could ever catch up to them. Light released today from galaxies just outside the Hubble sphere embarks on a journey with no possible endpoint. Each photon pushes onward toward Earth, while the space separating the source and the destination expands more rapidly than the photon can traverse it. Those photons will continue traveling endlessly through an ever-expanding emptiness, never arriving anywhere, never conveying their message about the distant universe they departed from. Even so, the Hubble sphere does not represent the final boundary for travelers. At this point, the difference between light and spacecraft becomes crucial. A photon moves at the speed of light from the instant it is emitted, never speeding up, never altering its velocity. A spacecraft, by contrast, can continue accelerating, potentially surpassing the local rate of cosmic expansion at its current location and pushing outward into regions where even light sent from Earth could never arrive. The true limit is set by the cosmological event horizon. This horizon, presently about 16 to 17 billion light-years away from Earth, defines the greatest distance any signal or traveler leaving today could ever reach, even with infinite time and unlimited speed. Beyond this threshold, cosmic expansion has already prevailed. Space itself stretches faster than any possible approach velocity can counteract. Destinations past the event horizon are not simply challenging to reach. They are fundamentally unreachable by any method consistent with known physics. The mathematics describing the event horizon arise from integrating the expansion history of the universe from the present moment into the infinite future. As dark energy continues to accelerate cosmic expansion, the event horizon does not stay fixed. It contracts. Regions that are accessible today will become permanently inaccessible in the future, as accelerating expansion carries them beyond the horizon. The opportunity for cosmic exploration shrinks with every passing instant. Current cosmological models indicate that in roughly 100 billion years, the event horizon will have collapsed inward to include only our local group of galaxies. The Andromeda Galaxy, now moving toward us due to gravitational attraction, will merge with the Milky Way long before this isolation is complete, but all other galaxies in the observable universe will have slipped beyond the event horizon. On far longer timescales, measured in trillions of years, this isolation becomes nearly absolute. Future astronomers living in whatever merged galaxy descends from the Milky Way and Andromeda will observe a universe containing only their immediate galactic environment. No external galaxies will be visible. The cosmic microwave background radiation, that ancient remnant of the Big Bang, will have redshifted beyond detectability. Every observable trace supporting the Big Bang theory will have disappeared. Those future observers may never realize that other galaxies once existed at all. They might build their physics and cosmology from first principles, seeing only their local stars, and conclude that their galaxy constitutes the entirety of the universe. The evidence for the Big Bang, for cosmic expansion, for the 2 trillion galaxies we observe today, will have been erased by the very expansion that carried that evidence beyond observational reach. This growing cosmic isolation imposes an urgent countdown on exploration. Every galaxy, every star cluster, every cosmic structure we might hope to visit has an expiration date, after which it becomes forever unreachable. The universe provides a limited window for exploration, and that window is steadily closing. Within these constraints, how far could a single human lifetime truly extend? Answering this requires combining the physics of time dilation with the geometry of an expanding universe, calculating not only how far a traveler might move, but how far the destination itself shifts during the voyage. At 99% of light speed, A traveler sustaining that velocity for 50 years of subjective time would traverse roughly 350 light-years. During this journey, Earth would age by about 355 years, while the traveler's own biological clock would record just 5 decades. This range includes perhaps 50,000 star systems, among them many stars similar to our Sun, and numerous systems already known to host planets. Within 350 light-years are stellar nurseries where new stars are forming, ancient globular clusters filled with stars older than the galactic disk, and a wide variety of stellar types, from red dwarfs that will shine for trillions of years to massive blue giants destined to explode as supernovae within millions of years. A 50-year journey at 99% of light speed would open access to cosmic environments vastly different from our local solar neighborhood. Increase the speed to 99.9% of light speed, and the figures change dramatically. At this speed, the gamma factor rises beyond 22, which means that 50 years experienced aboard the ship would correspond to more than 1,100 years passing on Earth. Within those same 50 years of personal time, a traveler would traverse roughly 1,100 light-years, sweeping through millions of star systems inside a region of space that could contain around 10 billion potentially habitable planets. The Orion Nebula, among the most breathtaking star-forming regions visible from Earth, sits at a distance of about 1,300 light-years. Traveling at 99.9% of the speed of light, a person could reach this vast stellar nursery, watch new stars being born, see protoplanetary disks slowly gathering into planets, and witness one of the most visually striking sights in our galaxy, all within a single human lifetime. They would arrive having aged 50 years, while more than 1,000 years had passed on Earth. Increase the speed further to 99.99% of light speed, and the gamma factor exceeds 70. At this level, the reachable range expands dramatically. It includes the Carina Nebula, a colossal star-forming region roughly 7,500 light-years away, reachable in about 107 years of ship time. It also encompasses the Eagle Nebula, home to the famous Pillars of Creation, located around 7,000 light-years distant and accessible within roughly a century of subjective travel. Even the galactic center itself comes within theoretical reach at these velocities. There, the supermassive black hole Sagittarius A*, containing about 4 million solar masses of collapsed matter, lies approximately 26,000 light-years from Earth. At 99.99% of light speed, a traveler could arrive at this immense gravitational focal point in roughly 370 years of ship time. A multi-generational crew that departed Earth when Rome was still a young republic would be arriving now, finding themselves at the very heart of the galaxy, surrounded by dense clusters of stars and violent phenomena unlike anything found elsewhere in the Milky Way. Pushing to even more extreme speeds drives these calculations into truly staggering territory. At 99.99% of light speed, with gamma exceeding 223, 50 years of subjective time would cover more than 11,000 light-years, carrying a traveler nearly halfway to the galactic center in what would feel like a long yet survivable journey. At 99.9999% of light speed, gamma rises above 707. In that case, 50 subjective years would span about 35,000 light-years, enough to pass the galactic center entirely and reach the far side of the Milky Way. Consider the implications. A person could, in theory, board a spacecraft, accelerate to an extreme relativistic velocity, cross the full width of our galaxy, and emerge on the opposite side, some 100,000 light-years from Earth, while experiencing the entire voyage as lasting only about 140 years of personal time. With hypothetical technologies that extend human lifespan, a single individual could roam the entire Milky Way, visiting regions forever hidden from Earth-based telescopes by thick clouds of dust and gas. If gamma factors climb into the thousands, intergalactic travel begins to edge into the realm of theoretical possibility. The Large Magellanic Cloud, a satellite galaxy of the Milky Way, orbits at a distance of roughly 160,000 light-years. At a gamma value of 3,200, a traveler could reach this separate galaxy in just 50 years of ship time, while 160,000 years passed on Earth. The civilization that launched the traveler would have risen, flourished, and likely disappeared long before arrival, yet the traveler themselves would have aged only 5 decades. The small Magellanic Cloud, at about 200,000 light-years, the Sagittarius Dwarf Elliptical Galaxy at roughly 70,000 light-years, and the Ursa Minor Dwarf at around 200,000 light-years all become reachable within extended human lifetimes at sufficiently extreme speeds. A traveler willing to endure a century of subjective time in transit could visit several dwarf galaxies, studying stellar populations that differ fundamentally from those found in our own galactic disk. The Andromeda Galaxy represents the ultimate challenge for relativistic travel within our local cosmic neighborhood. Located about 2.5 million light-years away, Andromeda is the nearest major galaxy to the Milky Way, a spiral system larger than our own and containing approximately 1 trillion stars. Reaching Andromeda would demand either impossibly long voyages at modest speeds or truly extreme relativistic velocities, where gamma factors climb into the tens of thousands. At a gamma of 50,000, 50 years of subjective travel would span 2.5 million light-years, exactly matching the distance to Andromeda. A traveler departing Earth today at this speed would arrive having aged 50 years, while Earth itself had aged 2.5 million years. They would emerge into a completely separate island universe, surrounded by unfamiliar constellations, orbiting an unfamiliar galactic core, and separated by an almost unimaginable gulf from anything that could be called home. What such a traveler might encounter there remains an open question, but Andromeda contains stellar populations both younger and older than those found in the Milky Way. Its central bulge is bigger and far more pronounced. At its heart lies its own supermassive black hole, estimated at 100 million solar masses, making it 25 times more massive than our own Sagittarius A star. The galaxy is surrounded by dozens of dwarf satellite galaxies, many of which host stellar populations and planetary systems that are completely unlike anything found in our local cosmic environment. Yet, the traveler would never be able to share these discoveries with Earth. Even if it were somehow possible to send signals back across 2.5 million light-years, those signals would still take 2.5 million years to arrive. By then, the civilization that sent the traveler would have faded into unreachable antiquity. In every meaningful sense, the traveler would no longer belong to the Milky Way, but would instead be a citizen of Andromeda. The journey would amount to a one-way exile into a truly alien universe. Increase gamma even further, and the figures expand to genuinely cosmological scales. The Virgo cluster, containing over 1,300 galaxies and located approximately 54 million light-years away, becomes theoretically reachable at a gamma value of 1,080,000. In that case, the traveler would age just 50 years, while Earth would experience the passage of 54 million years. Dinosaurs would have walked the Earth more recently than the traveler's departure would appear to observers remaining on Earth. The Coma cluster at 320 million light-years, the Perseus cluster at 240 million light-years, and the vast galaxy clusters that define the large-scale structure of the universe all fall within theoretical reach of a single human lifetime at gamma factors measured in the millions. A traveler could move among these distant cosmic cities, observe thousands of galaxies bound together by gravity, and witness the universe's architecture on scales that Earth-based telescopes can only capture in photographs. At the most extreme limit, where gamma approaches the billions, the mathematics allows for journeys spanning much of the observable universe within a single subjective lifetime. A traveler accelerating continuously at one gravity, then reversing thrust at the midpoint to decelerate, could theoretically reach the current observable horizon in about 45 years of ship time. They would age 45 years while the universe itself aged roughly 28 billion years. They would arrive at destinations that today exist only as ancient light reaching our telescopes, only to discover that those destinations had evolved beyond recognition over immense cosmic timescales. Even so, These extreme calculations eventually collide with the final boundary imposed by cosmic expansion. The event horizon cannot be crossed, no matter how great the velocity. Destinations currently beyond roughly 17 billion light-years will remain forever unreachable. Accelerating toward them only delays the moment when expansion carries them irreversibly out of reach. Even destinations that lie within the event horizon today may cross beyond it during long voyages. A traveler setting out toward a galaxy near the current event horizon could find that cosmic expansion during the journey has pushed the destination permanently beyond reach. The accessible universe shrinks even as travelers attempt to explore it. The one-way nature of extreme relativistic travel carries profound philosophical consequences. Time dilation allows immense cosmic distances to be crossed while aging very little, but it offers no way to return to the era from which one departed. Every journey becomes a one-way passage forward through time, with no possibility of return. Consider a round trip to the Pleiades star cluster, located about 440 light-years away. At 99% of light speed, the outward journey would take approximately 445 years of Earth time, but only around 63 years of ship time. The return trip would require the same durations. The traveler would come back having aged about 126 years, only to find that nearly 900 years had passed on Earth. The civilization that launched them would exist only as distant history. Languages would have changed beyond recognition. Political systems, cultural norms, and technological capabilities would all have transformed across nearly a millennium. The traveler would return as a living relic from a vanished era, perhaps honored, perhaps studied, but utterly separated from every human connection they once knew. Extending round-trip distances only deepens this temporal isolation. A round trip to the galactic center at 99.99% of light speed would return a traveler to an Earth roughly 520,000 years in the future. Modern humans have existed for about 300,000 years. The Earth awaiting the traveler would be separated from their departure by more time than Homo sapiens has existed as a species. A round trip to Andromeda, if it were somehow achievable at extreme relativistic speeds, would bring the traveler back to an Earth 5 million years in the future. 5 million years ago, the human lineage had not yet diverged from other great apes. Whatever beings inhabited Earth upon the traveler's return would be as different from present-day humans as we are from Australopithecus. These computations show that relativistic travel is unlike any form of movement humanity has ever known. The great voyages that shaped human history, the expeditions of Columbus and Magellan, of Lewis and Clark, of the Apollo astronauts, all preserved a living link between those who traveled and the world they left behind. Messages could be sent and received. Explorers could come home to families who still recognized them. The web of human relationships endured despite the vastness of distance. Relativistic journeys, by contrast, cut those ties completely. Anyone who departs Earth for faraway stars accepts a permanent separation, not only from their home planet, but from the historical moment they once belonged to. They become travelers through time, moving only forward, unable to return to the past they left behind. Even if they were to come back to the same physical location, they would arrive in a future that shares nothing with their former world except coordinates in space. This viewpoint reshapes the very question of how far a human being can travel. It becomes a balance between distance and connection, between the urge to explore and the need to belong, between discovery and return. Different people would choose differently, depending on what they value most. For one-way travelers prepared to abandon their past forever, the theoretical limit extends across nearly the entire observable universe. A lifespan felt as mere decades by the traveler could cover billions of light years, carrying them to the most distant galaxies currently revealed by our most powerful instruments. The universe allows exploration on scales that would dwarf even the boldest visions of science fiction. For travelers who hope to return and preserve some link to human civilization, the limits shrink dramatically. Returning within a few centuries of Earth time keeps open the possibility that recognizable human society still exists, but it restricts exploration to perhaps a few hundred light years. Even so, That range includes hundreds of thousands of star systems and potentially billions of planets. Yet it remains only a tiny slice of the galactic disk and an almost negligible fraction of the cosmos as a whole. The deepest meaning of these calculations lies in what they tell us about humanity's place in the universe. We live in a cosmos that permits journeys far beyond anything we once imagined. The laws of physics do not confine us to our solar system. They point toward routes to the stars, to other galaxies, to immense cosmic structures stretching billions of light years across the observable universe. The obstacles before us are technological rather than physical. They reflect our present inability to produce the immense energies required for relativistic propulsion, not hard limits set by nature itself. The universe has not built cages for biological life. It has left open loopholes capable of carrying awareness to the farthest edges of observable reality. A single human lifetime, measured in years as experienced by the traveler, could in theory include journeys that would humble the gods of ancient myth. From one small world circling an ordinary star in an unremarkable galaxy, a person could travel far enough to witness galactic superclusters containing thousands of stars, cosmic voids spanning hundreds of millions of light-years, and the filament-like large-scale structure of spacetime itself. And yet, these same results also expose humanity's deep isolation. Even with flawless technology, most of the universe will always remain unreachable. The cosmic event horizon retreats as we move toward it, driven outward by the same expansion that defines our era. The vast majority of galaxies we can observe have already slipped beyond any chance of contact. We can see their ancient light, but we will never set foot on their worlds. The 2 trillion galaxies within the observable universe form a record of cosmic inaccessibility. Perhaps only 1/1,000,000th of them, those within our local supercluster, could in principle be reached before expansion carries them past the event horizon. All the rest exists solely as images, light that has traveled for billions of years to draw pictures on our telescopes of places we will never visit. This perspective does not lessen the significance of reaching the stars. It places that achievement within the broader architecture of the universe. Humanity could grow into a truly interstellar civilization, spreading across hundreds or thousands of light years, settling planets throughout our galactic arm, and still occupy only an infinitesimal portion of what is accessible. We could fill the entire Milky Way and still amount to a single grain of sand on an endless beach. In the end, the question of how far a human can travel in one lifetime becomes a question of what kind of journey we are prepared to choose. Physics allows for almost anything. The real obstacle is engineering, which remains ours to overcome. Yet even beyond technical challenges, choosing a destination also means choosing what kind of beings we want to be, how we define connection, and what exploration truly means. A voyager who sets out for Andromeda accepts a journey that goes only one way, into a universe that is no longer familiar. They will never again see a human face that belonged to their original time. They will never be able to share what they discover with the civilization that enabled their departure. In practice, they would become the beginning of a new branch of humanity, planted in distant ground, separated from the living tree that gave rise to them. Perhaps some travelers would find deep purpose in that kind of cosmic pioneering. Perhaps knowing that human awareness had expanded beyond its home galaxy would be enough to justify any personal loss. Perhaps standing inside Andromeda itself, surrounded by its trillion stars, would outweigh everything that was left behind. Or perhaps the human spirit depends more on connection than on exploration. Perhaps the most meaningful destinations are those that still allow a return, that keep the threads intact between travelers and home, that preserve the chance to share discovery with those who did not leave. These questions do not have universal answers. Different people will choose differently. Some will press onward toward the event horizon, chasing the most distant limits accessible to human consciousness. Others will explore nearer regions, weighing awe against connection, distance against the possibility of coming back. The universe is indifferent to these choices. It provides the same physics to every traveler, the same time dilation at every speed, the same cosmic expansion in every direction. What we choose to do within those boundaries is entirely up to us. You exist within a universe that spans 93 billion light-years, filled with structures so immense that light itself needs billions of years to cross them. From your place on a single small world, you look out toward distances so vast they require numbers with 24 digits just to express them in miles. This scale goes beyond everyday experience and even beyond the limits of human intuition. We cannot genuinely grasp how far the universe reaches, and yet, within the span of one lifetime, properly equipped with technologies we can envision but have not yet constructed, a human could, in theory, traverse meaningful portions of that staggering immensity. The universe has not erected walls around humanity. Instead, it has laid down highways extending toward every horizon, routes we have not yet learned to travel, but that physics itself declares open to anyone capable of achieving the required speeds. How far a human could actually go in a single lifetime depends on what we are prepared to build, to give up, and to invest across generations. It depends on whether we prioritize distance over return, exploration over connection, discovery over belonging. These are decisions physics cannot make on our behalf. They remain deeply human choices, even when their outcomes unfold across cosmic scales. The stars are not unreachable. They are simply waiting for us to develop the means to approach them. The galaxies are not permanently beyond our reach. They require only enough velocity and enough willingness to accept the time-related consequences of the journey. Within the equations that describe motion through space-time lies a promise that distances measured in millions of light-years could one day be accessible within a single human life. That promise is written into the mathematics of relativity, confirmed by a century of experiments, and waiting for the engineers who can turn theoretical possibility into practical reality. The universe invites exploration, and somewhere between the 430,000 miles per hour we have already achieved and the extreme speeds where gamma rises into the millions lies a boundary where human exploration of the cosmos shifts from imagination into committed fact. The distance a human can travel in one lifetime is not ultimately constrained by physics. It is limited only by our imagination, our resolve, and our willingness to pay the cost the universe demands for passage to the stars. If these ideas resonate with you, if thinking about our place in a vast and indifferent universe sparks curiosity rather than fear, then this channel is for you. Take a moment to like the video so more people can find these conversations. Share your thoughts in the comments about how far you think humanity should go, and subscribe if you want to keep exploring the cosmos together. Every interaction helps build a community of people who are willing to question, to wonder, and to look outward with open minds. Until next time, keep looking up.